Hey Zarahoon, thanks for joining us. You're actually the only other one on the call right now, so we'll give a few minutes to see if a few other learners join us today.
انا ماكينه نتكلم.
Hi, welcome. Got a small group so far today, so just giving a few minutes to see if other learners join as well. If you have any specific questions that you want to talk about today, feel free to, we'll just type them in the chat today, or raise your hand and we can go ahead and get those noted for the session today. Right. We have a small group today, but I'm okay with that. I want to thank you both for choosing to be with us today. And we might just have plenty of time today for questions or open discussion on any of these topics. So again, please feel free to type any questions in the chat or just raise your hand, unmute. We can have a lot of, again, open discussion today. And hopefully some others will join us as we go along. So thanks again. I think everyone here has been doing office hours before, but just a reminder that this is a time to ask and answer questions. So again, easy, open discussion today. And quick reminder, we are in the final week of the course. So covering everything solar array design, and then wrapping up everything that we've learned so far. So are there, I'll just go ahead and start. We have, again, like normal, some review questions we can go through, but are there any questions to start us off today? And if they come up later, that's fine too, but um, any particular questions that we want to talk about today? Well, if a question comes up at any time, feel free again to just raise your hand or type it in the chat. Let's see. This is the kind of poll we usually start these off with. I just want to get a gauge of where we are on some of these. These are the big topics for the second half of Unit 4. So estimating your starting configuration for a solar array, calculating the power output of that solar array, checking and adjusting the power requirements, and then estimating water production. See how everyone's kind of feeling about these topics, and then we'll kind of maybe guide our discussion based on which ones are lower confidence. So we can make sure we cover those. Looks like maybe we're kind of middle of the row for some of these topics. Um, Zerahun, I see your hand up.
Okay, thank you very much, Jessica. Good afternoon, everyone. Sorry, I'm joining you from my mobile device, and it's a bit difficult. It's not practical.
Sure.
I have one question regarding hourly water production, which is the final step of this module. When we calculate the hourly production, first we plot the graphs, the system curve, and also the graph for each frequency. For various frequencies, we plot the graph, and also we plot together the system curve. Then the points, the system curve crosses the frequency curves are the hourly production values. But when you plot it, you can clearly see from the module there are points the system curve misses, or which does not cross the frequency curves. But the hourly values are calculated already, even for those points missing in the module. And I don't understand how these values are estimated. Yes, for the points which are crossed between the system curve and the frequency, okay, we can read it from the graph. But for those points which are not crossed or in between, how did you estimate it? Yeah, other than extrapolating to find these values. Thank you very much.
That's a good question, Zerahun. So if it's not crossing, then we shouldn't have a value for it. So if there's a specific diagram that shows a value for a time of day where the frequency curve does not cross the pump curve, then could you let me know which diagram that is? Because it shouldn't give a value. If the two curves don't cross, it means that there's going to be zero production for that hour of the day. Um, so it should only be the points. We should only get hourly production for points where the system curve is going to cross the frequency curve that we've adjusted. So yes, you have a good point, and it shouldn't have a value for it. Um,
Sorry, Jessica, if possible, can you put on the screen the graph calculated for the on the module to calculate the hourly values, if okay, with multiple
yes,
frequency
I can.
curves. Yeah.
Yes, I can put that up real quick. Let's see. Can you see the design tool now? Okay, so as an example, this is the one for Zamburi. So you'll see that down here we do have some frequencies, but what we've entered for those hourly productions for those frequencies is zero, um, because it's not actually crossing the pump curve.
Okay, so just to make it clear, uh, for those points which does not crossed by the system curve, the hourly production is zero. So there is no hourly production on that point. But for those points crossed by the system curve, that are the specific hourly productions for each frequency curve. And for the middle pointers, of course, I know we will extrapolate and find the values. This is the way we did it, yeah?
Yes, and so these all the points that do intersect the curve, um, those you can do visually. Um, is the simplest way, just a visual check of what the flow will be just by going straight down. Um, yeah, visual check is the simplest way to estimate what your production will be.
Okay, all clear now. Thank you very much, Jessica.
Of course, thank you. That was a great question to start the day. For anyone who's just joined us, we just have this poll up. I see several of you have answered it. So we've got this poll up to see kind of where we are on the topics for this week. So it looks like maybe we're lowest confidence on estimating a starting configuration for a solar array, and then a little more confidence on other areas. So we can just go through our review today because we cover all of these topics in some of these review questions. And if you have particular questions on any one area, please make sure to raise your hand or type in the chat as we go. All right, let's see. Okay, here's a question to start us off. When designing a solar array, what pump and or inverter requirements must we pay close attention to? These are kind of the foundation for our solar design. Yeah, good responses. So a lot of votes for all of the above. Yes, they're all important. Motor power, yes, very important because we are ultimately trying to get our array to meet the motor power that we need. So that one, yes, is very important. But voltage range and current are also important for how the pump will operate and making sure that it's going to operate correctly. As we go through the material today, and as you've seen in Unit 4, if you've already done that, each one of these will be affected as we add panels to our array, and that is what can help us decide how many panels to add and how to add them. So yeah, we want to meet the pump's power while also remaining within any limits, so current and voltage limits that our pump might have. Current being a little bit of a unique case because it's going to draw the amount of current that it needs, and we'll talk about that in a few minutes. Okay, so there are two different ways that we can wire panels in series. We call this or wire panels together. One is in series, one is in parallel. So when we um, wire them in series, what are we increasing? Yeah, so a lot of votes for voltage. So yes, when we wire panels in series, we are increasing the voltage. So that would be the top figure here in our diagram. So we're connecting um, panels together, kind of in a positive to negative um, wiring. Kate, I see your hand up.
Yeah, just a question more about feasibility. So I know when we're choosing an arrangement, we may want to put X panels in series or like certain strings, but to reach the necessary electrical needs. But what about when you think about like construction feasibility? Like, is it really feasible to put 15 solar panels in an array if that's not like if that's what the design calls for, but that's not really a feasible way to construct it. Like how do you start bringing in like construction feasibility when you begin thinking about these arrangements?
Mhm. That's a really good question, Kate, because that's right. That's something we have to think about as well. So on one side, something to think about when you're designing, if you know you need multiple parallel strings, is it typically works out to have like an even number of total panels, right? So we can have maybe a um, two strings. So if we have two strings, it works out better to have maybe like an even number of total panels because that allows construction to be a little bit easier, being able to do even numbers and not have something that's like, here's four panels and here's five panels. That doesn't help our project very well. Um, and then, yes, thinking about how they will be racked together. You can do a pretty high number of panels in series. Or we'll say in a rack together. So I think I've seen up to 14 panels. I'm sure some places have maybe done more, and that is just going to come down to how they design their racking system and how many supports they put into it. So um, yes, I've seen it. Like I said, personally, I think I've seen up to 14 panels in a rack together. And then for very large projects, you'll just usually see multiple um, solar racks holding up maybe 10, 14 panels. But then when they get down to their electrical boxes, they'll be combined in a way that is either in series or in parallel, depending on the design. So in those situations, what you'll typically see is maybe if there's three separate racks to be able to hold that many panels, those racks would hold panels that were in series together, and then they would combine those three separate racks in parallel, and those would be the parallel strings. Um, I wish I had a picture for you. I'm gonna look really quick, but this is a good question. If anybody else has tips for like large arrays and how those get built, practically, please feel free to jump in. I'm going to look for a quick picture. So here's a fairly good one. So you'll see, let's see. They've got, I think, 9 panels across, and so 2 rows of 9 panels across. But they've just used multiple racks to get as many as they need. So they're likely either using, it's possible one, two, probably my guess is 6 parallel strings in this project, and that each row would be its own string of in-series panels. And then they've got them all wired up kind of underneath when they get into their combiner boxes, got them all wired correctly. Does that help, or do you have any kind of follow-up or clarifications on that?
Yeah, that's helpful. I guess I was reviewing a design that we're about to start, and it was saying that we're going to have one string of 15 solar panels. And I'm just thinking like site arrangement and everything that seems complicated because I've seen more like of the solar panel racks that kind of end up more in like a square looking configuration because you have roughly a similar amount in parallel versus series, but like one string of 15 seems a little hectic to me. I don't know. I mean, this is 9, I guess, with 2, but I was just curious about that.
Yeah, that's a good point. 15 is a lot, yeah. If you guys can adjust your design to like 14 or 16, then you can you can kind of do it like they've shown here, and just do like 7 across or 8 across and have 2 rows, and that would be your string. Because it just depends on how you wire them underneath. But yeah, that's a good question. 15 is probably a lot to have, just again, depending on your construction abilities in the location that you are. That's a great question. Thank you. Okay, so this one will be a little bit of an opportunity for some open discussion. So what happens if the voltage produced by the solar array is too high or too low? So we just saw that wiring panels in series increases the voltage. And so what happens if we don't get enough or we get too much? I've seen some discussion on this in the WhatsApp community this week, so wanted to make sure we covered that. Oh, and Wesy, I see your comment in the chat as well, suggesting that if you have an odd number of panels, you can add an extra panel and either connect it or not, just to make that construction a little bit easier for the even panels. Thanks, that's a great tip. I appreciate that. Okay, anyone want to share what happens if we get voltage too low, too high? Okay. So yeah, voltage being one of the limits that we have to make sure that we pay attention to, because the pump or the inverter is going to have trouble if we're outside of that range. It has kind of a sweet spot where it can operate, and if we don't have enough, then it's likely not going to start. Then again, if it's too high, the pump is likely going to turn off or be damaged, even in some cases, depending on our protections of the system. So we really have to make sure that we're in their range, in that our solar array in that case needs to be designed to be within the range of the pump's limits. Okay, so if we just looked at voltage. So if we are combining panels in parallel, then what increases? Yeah, lots of votes for current. So that's our other option, right? Those are the current and voltage being the two factors that go into our overall power. So wiring panels in parallel is what helps us increase our current. And so this is another way that we can ultimately increase the power of our solar array. So our general recommendation would be to add panels in series first to get into the voltage range that we need. Preferably the higher end of the voltage range. And then after that, if we still need more power, to add strings of parallel panels to increase the overall power. That can help us keep the overall current of our array a bit lower, and that just helps improve the efficiency of the solar array. So increase voltage first as much as you can, and then increase current until you get the power that you need. Okay, so this is the one that we've had more questions on. So what happens if the solar array supplies more current than the pump needs? Anybody want to share? It's okay. This is, like I said, this is the one we've had the most questions on. Zerahun, yes, please.
Yeah, thank you, Jessica. Like you said for the case of the voltage, the pump motor has a limit for the voltage, which is the input voltage range, and also the limit for its the current draw, to which limit the pump motor can accept the current. If it is beyond its rated current, it's going to have a problem on the motor of the pump. I think it's the same. The principle is the same as with the voltage. Thank you.
Thanks, Zerahun. Yes, so the pump currents can be a little bit different. A little bit different than what we see with voltage. So we do want to make sure that we protect our systems from like extreme overcurrents. So things like short circuits and all of that that could drive like a really high current through our system because of an electrical problem, an electrical hazard. And so we can use fuses and breakers for that. But during normal operation, our pump is actually going to draw the amount of current that it needs. So the pump is going to dictate how much current it needs. So we can think of current rather as being like pushed and supplied by the solar array. We can think of it being load driven or pump driven. So based on the flow in the head and the amount of power that the pump needs, it will choose kind of how much it needs to draw, and it will do that. And so I've seen that in the chat a little bit. So Wesley says that the extra current is wasted. That's kind of true. So if the pump doesn't need the extra current, it's just not going to take it. And so, yes, it's kind of a balance between making sure that our system's protected from extreme cases, like again, short circuits, because that kind of forced current is not good for our devices. And that's where we get fuses and breakers and overcurrent protection. But again, on a normal operating day, our pump is going to decide how much current it needs, and it's going to pull it. That's the main factor that's going to increase or decrease the power to our pump, is it's going to pull more or less current, whereas the voltage is fairly going to stay the same for the most part during the day. So yeah, so two different cases. So that's why we typically will see that our current in our solar array is higher than maybe our pump, or can be higher than our pump. But we do want to make sure as well that our even our inverter rating is higher, just to help with the smooth operation as well. I think this is our last poll, your last poll of the whole course. So what's the final step in SPWS design? Yeah. So the majority of us voted for compare water production to the demand. So I would agree that as far as design goes, that yes, that would be our final step. Everything else probably falls into maybe like a construction or procurement phase. But as far as design itself, and what we're learning in this course specifically, our final step will be to compare um, our estimate of water production to what we said our demand would be. So kind of linking our final step with our first step, which was our water demand. And so we want to make sure that we are within our limit. And so the IEC standards say that we need to be in a range of -5% to positive 20% of that water demand that we calculated. And then that can help guide that, we've gotten a design that is in the right range and is good based on what we said our demand was. And so I've seen, again, some questions, and we've had one question today on water production and how we estimate that. I've seen a few more of these questions in the WhatsApp community this week. So we can talk through these as well today. And then again, if you have any specific questions, either about water production or anything else from Unit 4, please feel free to raise your hand or type that in the chat. And we should have plenty of time today to cover questions. So for solar pumps specifically, solar pump curves already have the power built into their curve along the bottom axis. If we'll remember, that's the biggest difference between a solar pump curve and a traditional curve. And so what we can do for solar pumps is it's a little easier. We can just kind of work backwards. Usually when we look at a solar pump curve, we're finding our TDH and our flow, and that gives us the power we need for our pump. But in this case, we're getting a power that our array can produce throughout the day at each hour, and we can use that to work backwards. So we would maybe at noon, our power is 2.3 kilowatts. So we'd find that on the curve. We'd go straight up to whatever line matches our TDH for the project. And then we can go over to the left to match that up with our flow that we'll get at that hour. And so you do that for every hour of the day that you have power coming from your array. And that will give you your total production for the day if you add all of those up. There may be cases where maybe your power doesn't line up with one of the TDH lines. So this curve actually is maybe not a great example of that. But in some cases, you'll have where your TDH lines don't go all the way across. And so if your power doesn't line up with the TDH curve, that would be an example where there would not be flow at that hour. So it has to hit one of the curves in order for there to be flow at that hour for the solar pumps. Are there any questions about how to do this for solar pumps? or why we do this. What's the point? That's okay too. Again, our main goal with this is being able to estimate how much water our array will produce for us, and so we can compare it to the design demand. All right, and then for AC pumps, it is a little more complicated because we don't have curves that show us what power is at different conditions. And so this is where we go through the process of using the affinity laws to adjust our pump curve. And so that's what you'll see in this diagram is we have the blue line is our system curve. And then all of the other lines are adjusted pump curves. So typically a pump manufacturer pump is going to be rated for either 50 or 60 hertz. In our example, it's 50 hertz. And so, but we don't always get to operate at 50 hertz in a solar project. So with AC power, we always get that full 50 hertz. But with a solar project, as the sun rises and sets, the frequency that our pump is running at is changing with the different amounts of voltage and current that we have. So we're not operating at that, what we might consider a full power state. We are running at an adjusted power because we just don't have as much from the solar array. And so that's where we use affinity laws, and we can calculate the flow rate and the head at lower power based on what our full power curve says. So I know that those equations can get a little bit confusing and a little bit tricky looking at the two different states. We can talk through that too if that's helpful. Your design tool does do that for you. And so you won't have to hand calculate those. It is just important to kind of understand what's happening with those affinity laws and why we want to use them. And the biggest thing is that affinity laws allow us to compare different operating conditions for a pump. And so we can use our known conditions, which is the manufacturer curve, to determine maybe a lower power state during the day, a new condition. And then once we've done that, we just can use a visual check with the graph to help us know what our daily production is going to be. So again, anywhere that you see one of your frequency curves cross the system curve is going to be the hourly production for that hour of the day. And so you will add all of those up to get your daily production. If the frequency curve, so these curves in the lower left-hand corner, if they don't cross your blue system curve, then you won't have any production for that hour of the day. It just means the frequency and the power available from our solar array is just not high enough for that pump to have production at that hour. Any questions about either affinity laws or water production for AC pumps? Yes, Wesley, I see your hand up.
Yeah, so I still get confused how we come up with the curves for the frequencies. I know when we use the formulas, we end up calculating the flow at that hour. So how are the curves coming about? Because like for the pump curve, the system curve, it shows how the pump is operating based on different flows and TDH. But for the frequencies, how are the curves coming about? What are we using to come up with those curves? Because we can only calculate just one flow when we use the formulas. Yeah.
Yes. So yes, in the course when we go through the examples, we're showing, you're right, 1 point. But in order to have a curve, we need lots of points, right? So I'll show you a quick section Really, it's a lot of calculations when you actually want to show this. Um, and that's where hopefully the design tool will be very helpful for everyone. So if you scroll down below your curve in the design tool, you can see where we have done these calculations for each curve. So, so for example, this one at 8 in the morning, this is the data we're using for our curve. And so what we've done is we've used the affinity laws 1, 2, 3, 4, 5, 6, 7, 10 times, 10 times for flow, and then 10 times for the head, all for 8 a.m. And so we are basically creating our own new curve for each hour of the day. And so, but we're using the same process that we've shown in examples in the course for those affinity curves. We're just doing it again multiple times throughout the day based on our frequency, and then we can get our flow in our head. And so you'll see that there's a down here is a big table, but each one of these kind of side tables, these section tables, is a frequency curve for your day. And so that's again where it's we've built that into the tool for you. So hopefully that's helpful for you. And then it's just good to know kind of the background of how those are being created. So hopefully that helps. Kate, I see your hand up as well.
Yeah, can you remind me, how do you determine the frequency intervals again? Like, where did you get the 8.5, 27.6, and so on?
Mhm. Yeah, good question. So those come from up here. It's one of the values that we calculate throughout the day. And so we use our power. It's one of the affinity curves as well. It's actually the first affinity curve equation that we use. So we can relate frequency to the power. So we can take our the power we have at 50 hertz and we get that from the manufacturer, and we can compare that to our derated power. And so that gives us these frequencies. We do have to adjust sometimes if they exceed 50 in this case, which is our top range from our pump manufacturer. So you might have to bump those down to 50. But then these values all get pulled down here. And that's what we're using then to get flow and head.
And the adjusted values, that's only if you would go over the manufacturer specs. There's no other adjustment you need to make to those values.
Correct. Yep. So in our
Okay.
example, our pump is 50 hertz. You might, depending on your location, have a 60 hertz pump. And so then you would just make sure it doesn't go over 60. Exactly. Let me pull up one more thing that might be helpful. I put one other diagram for the affinity curves in the WhatsApp group this week, but I know some of us may not have seen it, and so this might help. So this is again, this is the same thing that we're doing in our course. It's just written a little bit differently, so it might be helpful just to hear it a slightly different way. So yes, so the first thing that we're doing is we're using affinity laws, specifically the one you see down below the first box, to calculate our frequency. And so that's what's happening in that big table, is we're calculating our frequency. So to do that, we need what the pump manufacturer says our frequency is for the pump, and then what they say the power is, which is something that we found in step 4 of the process when we were looking at our pump. So those two numbers, and then again, we need our derated power at each hour of the day. And that'll give us a new frequency at each hour of the day. And then our second and third, or second step is we're calculating the flow and the head for each of those hours and each of those frequencies. So those are all the tables that you can see at the bottom of your design tool. So again, it's a lot of calculations. I would never expect you to do them all by hand on your own. That's why we build them into the tool. But just again, so you understand how it's being done, that's what we're doing. And it's kind of very repetitive. Again, we've used about 10 points because that helps us get a nice, good curve. You could do more or less, but I think we've done 10 in our tool to get a nice, smooth curve. And then again, the final step will be using those to plot that new adjusted curve so that we can see where they match up, where they line up. So, any other questions on, let me go back to this one. Any other questions about how we're using the affinity laws or plotting them? I know that this is one of the trickier portions, but again, keep in mind we're doing this mainly so that we can estimate our water production for the day is the big goal here. But I know that it is a lot of calculations and they get very repetitive. All right, well, good. If you have, again, if any other questions on that come up, feel free to let me know or reach out in the WhatsApp community. I'm actually just going to jump ahead real quick. We just looked at the tool a little bit. Has everybody completed your step 5, B, and C? So it's kind of the end of the design. Maybe just react with a thumbs up if you've completed that yet. And then have there been any challenges with that portion of the tool? Okay, cool. Kate's got it done. Thanks. I know that having to adjust certain values can be a little tricky. So the frequency for AC pumps, and then it's current that we adjust for the solar pumps. And both of those are doing a similar thing where we have to adjust it to the limit. And I'll just clarify again, based on some discussion I've seen in the WhatsApp community, when we say that we're going to adjust the current or adjust the frequency, we only mean in our design. We don't mean that we're going to manually adjust it when the project is installed. You might have controllers who can do some of those adjustments. They can control the frequency if you needed to. But when we've talked about it in this course, we just mean that we're adjusting these values in our design tool to get an accurate picture of what our water production will be. So I know there's been some confusion when we say we're going to adjust the current. We're not manually adjusting the current on the pump itself. We're just adjusting our design to reflect what the pump is going to do. And that's because the pump is not going to draw more current than its rated value. But sometimes our calculations don't know that, and they're going to say that we have more current than our pump can do. And we want to make sure we adjust that so we get an accurate picture. Wesley, yes, please.
All right. So for the variable frequency system for the inverter, in this case, does it mean that when we adjust it, it has to start at the lowest frequency that is able to generate flow?
That's a really good question. Yes. So some of our
Well done.
inverters will, yeah, some of our inverters, they run off a variable frequency drive, and you can set the frequency range within those inverters or in those drives. And so, yes, I know a lot of engineers who will choose to set the minimum frequency at what we're seeing, or maybe just a little bit below to give a buffer, but you can set the minimum frequency where you know that your pump's not going to be able to produce water anymore. And so we can get that from our design tool and then be able to set that minimum frequency. And that just helps our pump not try to start when we know it's not going to be able to pump water. And that can just help our pump operate a little bit better. You can compare the frequency you get in your design for no flow with what the pump manufacturer says is the lowest frequency. Typically, they'll recommend a lowest frequency, and you can look at that as well and kind of compare and then set that in your project. Kate, I see your hand up.
Yeah, so like for this example here, does that mean you would have to like extrapolate between it looks like hour 8 and hour 9 to see when that production starts? And that would be where you set your drive.
You could, if you want to be really detailed, you could do that. You could also set
Okay.
your drive at 27 hertz, as long as that doesn't go below like the manufacturer's recommendation. You could set it at
Okay.
27 hertz. Again, our calculations won't be perfect, and so it's possible we have some wiggle room anyway. But yes. Zarahoon, I see your hand up as well.
Okay, thank you, Jessica. Just one clarification from you. For these two cases, for the solar pump, which is for the DC pump, and for the for the AC pumps, we already working on. For the case of the solar pump, after we go through all the steps, finally we compare whether the voltage and the current of produced by the array are compatible for the motor, or the motor, let's say for the motor current and voltage requirements. But when we come to the AC pump with an inverter, we compared the output of the array with the inverter requirements. Why is that? Why not with the motor?
Yeah, that's a good question there. So when we're working with an AC pump, it's going to have a single AC voltage that it can accept. And so what our inverter is doing is it's taking our range of DC power that we're getting from the array, and it's converting it into an AC power source that is then being sent to our pump. And so the AC power that it's providing will always be at one voltage, at an AC voltage. And that will depend on what your inverter is rated for. So in our example, we chose an inverter that has a 380 volt output voltage because that is what our pump needs, the pump that we selected. So it's the inverter in this case that can take the range of DC voltages from our array and it converts them to a single AC voltage, which is what our pump gets. And so in this case, it is the inverter that we need to pay attention to. Solar pumps are similar in the fact that they just have the inverter built inside them. And so we look at them as a whole unit, but they're kind of doing the same thing. It's just all that inverter is kind of built into the DC pump. So we think of them as just one unit and just call it a solar pump. But with the AC pump, it's really two separate pieces of equipment that we have to look at. And the inverter is what takes the solar array power. Does that help? Awesome. That's a great question. Okay, I am gonna hop ahead just a little bit, just because I want to make sure everybody sees this. I know some of you on the call have already finished the course, which is great. Congratulations if you have. If you still need some time, we're going to give one more week for everybody to wrap up what they need to. So you'll have till May 17th. So if you have quizzes or discussions or learning material to do, please make sure you finish that by May 17th so that you get a certificate. After May 17th, you'll still get access to the learning content. So if you want to go back and review anything or download anything again, you'll have access, but you won't be able to earn your certificate after May 17th. So if you need any help or have trouble, reach out to me. Again, the final exam is still having some issues with grading. So if you pass it, please don't take it again. Just let me know and I'll make sure it gets updated for you. Yeah. Okay. Any other questions can be from Unit 4 or from earlier in the quiz or earlier in the course. Kind of the whole design process that we've gone through over the last 5 weeks. Any final questions? Okay, I see a comment in the chat about struggling to understand the VOC and the VMPP. So I'm not an electrician, so I may not give the best answer, but VOC and VMPP are specifications that are given to us by the solar panel manufacturers. Basically, one is the voltage that you would see at maximum power. And so that's the voltage we pay attention to a lot. But then VOC is the voltage we would see if there was like an overcurrent situation. So if there was a short circuit in our system, that's the voltage we would want to see, or that we would see in like a short circuit situation. And so we want to make sure that we're mindful of both of those, just in the event that we have a short circuit, we don't want to overload our voltage too much. But the VMPP is our kind of more of our normal operating conditions, what we would see at maybe like a maximum power condition. And so, yeah, there are just a lot of different specs that we can look at in the project. I know there's been confusion too about which one you use when you're estimating like minimum and maximum number of panels. And so I would say maybe don't get too caught up in that because those are estimates. And so I always have to remind myself. So if you have to remind yourself too, it's okay. But VMPP for minimum number of panels and then VOC for maximum number of panels. And that's the recommendation. Again, that helps us to determine, okay, in like the highest voltage we see, then what's our minimum number? And then in our lowest voltage, what's our maximum number? And it gives us a range. But again, there are different ways. This is one way to determine your number of panels. There are other ways. And we're always going to check our design in the end, right? So if we make a mistake, we estimate too many or too few panels, then we can estimate that. I can check and see if I think I can release this PowerPoint. This is from Water Mission. And I'll just verify that I can release this to everybody. But yes, we can send this along as well. If not, I'll make sure that the same information gets to you. But Water Mission is usually pretty generous in what they're willing to share. And so, yes, this is all the same information, but it's just written a little bit differently. So I know sometimes seeing it slightly differently from how you've seen it in the course can be helpful And so, yes, I'll send that out, Kate, if I can. All right. Any other final questions? I know we're at the top of the hour, so if you do have to if you have to go, just thank you so much for being here. But are there any other questions that anyone has? Yes, Kate.
Yeah, or even if you have like similar PowerPoints or the other steps in the process, that's just a nice way to review the materials in a different fashion. And if you could also share those, that'd be helpful.
Yes, I do have one for every step, and so I'll ask
Okay.
and then send those out. Yep. Okay. Well, hearing no other questions, we'll go ahead and close today's call. This is going to be our last webinar, so we won't have one during our bonus week next week, but the WhatsApp community will still be available. And of course, you can reach out to myself or Christian on the learning platform if you're having any challenges. We're going to be here to support you until you get everything wrapped up. So if you have questions after today, again, just put them in the WhatsApp community or message us through the learning platform. Um, and yeah, again, you'll have another week. So May 17th will be the final deadline to get your certificate. So thank you all so much. We really appreciate you taking the time to join us today and hope you all have a great weekend. Thanks, everyone.